So hello everyone, I'm excited to present our work that brings high-level programming to application networks. And this is a joint work with folks at Duke and UCLA. Microservices have become the de facto way to build and deploy cloud applications today. In this architecture, applications are split across anywhere from tens to thousands of microservices. And this communication of microservices rely on RPCs that run over the network. Here we show two services, A and B, where service B have two replicas. We refer to this RPC level layer 7 communication as between microservices as application networks. And to manage this network, developers use application network functions, or ANFs, which implemented features like traffic management, policy enforcement, and security. Today's application network are enabled by service meshes like Istio. In a service mesh, ANFs run on different platforms. Some run inside the RPC library, and others run in a sidecar proxy that is co-located with each service instance. And finally, some may run in a remote proxy similar to middle boxes. According to a recent survey, almost all cloud applications today use service mesh. However, service mesh suffer from two major challenges. First, it imposes a high burden on developers. Let's say if a user wants to run 3 functions for RPC traffic between service A and B. A logger that records all RPCs, a firewall that blocks certain users, and a rate limiter that limits the request from service A to B. The developer may end up putting the logger in a sidecar, the firewall inside the middle box, and the rate limiter inside the B sidecar. Now they have to write each function in whatever language that the platform supports. For example, it's Rust for sidecar and Go for the RPC library. And even if some functions may be built in, developers often have to modify the application code just to pass along the right information. And the second major challenge is it has high performance overhead. Right now, the developers have to manually decide where to place each function. However, where and how ANFs run has a big impact on performance and correctness. Take the RPC libraries as an example. They have the lowest processing overhead because they directly run within the application. But it also means that it cannot be used with untrusted code. Now let's look at the rate limiter. It's supposed to limit the total number of requests from service A to write all replicas of service B. But because it's running on the service B side, we end up with one rate limiter per service B instance. Now they have to keep their state, which is the token bucket, synchronized to guarantee correctness. So indeed, prior studies show that today's service mesh can increase latency and CPU usage by up to 7x. And note, there's actually a better configuration for this. The logger is now security sensitive, so we can move it to the RPC library for lower overhead. We can also move the rate limiter to the middle box, and that way there's only one instance. We don't need to synchronize their state. However, such optimization is hard to do today because application network implementations is both low-level and platform-specific. Our goal is simple. We want to make application networks easy to use and highly performant. And in this work, we focus on the programming of the data plane, which has more complex and performance-sensitive processing. To realize our goal, we built AppNet. The core idea behind AppNet is to separate what the network should do from how it's implemented. Developers write what they want the network to do in AppNet programs using a high-level abstraction. And the AppNet compiler takes the AppNet program and the RPC schema defined in languages like protobuf, then it analyzes the input programs and automatically decides where each ANF should run for both performance and correctness. It then generates platform-specific code that developers used to write by hand today and then deploy them onto the corresponding platforms. And finally, there's the AppNet controller that handles everything at runtime, including workload changes, failures, and configuration updates. Now let's take a closer look at AppNet programming abstraction. We model RPC processing between a pair of microservices as a chain of elements, and each element performs a single network function on RPCs. Here's how you write the example from earlier. This chain captured the execution order and the semantic of the specification, but it does not require the location to be specified. And let's say the developer can still provide location preferences when needed. And inside each element, AppNet uses a generalized match action abstraction. You can match on both RPC fields and elements' internal state, and define actions to forward, drop, or lock the RPC. It's more powerful than traditional match actions like in P4 because it works at RPC level and supports stateful and consistency-aware processing, which I will discuss later. Here is the request processing code for the firewall element. Its job is to block certain users. Here, it first extracts the username from the RPC and then get the permission from the firewall rules table. We then match on the resulting permission. According to the permission, we'll either forward it or drop the request with an error message. We chose match action because it is simple, composable, and easy to optimize. To facilitate stateful processing, AppNet provides shared state abstraction with configurable consistency levels. Currently, AppNet supports strong and weak consistency. Weak consistency means eventual consistency where the state synchronization is moved to the background. It has better performance, as I will show later. So for the functions that do not require strong consistency, developer can get better performance. And here is the full AppNet program, a grammar, and please check out paper for details. Next, let's talk about AppNet compiler. Its job is to optimize the configuration while preserving the semantics. For each element, the compiler must decide which platform to use, the location of elements, and their execution order. Note that the compiler can reorder or relocate elements if it yields better performance. However, there are two major challenges that AppNet compiler must address. First, when optimize the chain, the compiler needs to preserve the semantics of the input specification. This is especially important for some elements that are stateful, as reorder or relocating them may change the behavior of RPC processing. Second, the search space of the optimization algorithm is huge, especially as the number of elements grows. And in this talk, we'll focus on how we ensure semantic equivalence during optimization, and for details on how we efficiently navigate the search space, please refer to our paper. Here's a simple example that demonstrates why preserving semantics is tricky. Let's say we have two elements, a firewall and a logger. The blue boxes represent the processing logic, and the green boxes show the internal state. Here, the logger keeps a log of the RPC it sees. Let's say there are two RPCs coming in, and the firewall drops the first RPC. A naive compiler may try to reorder the elements. Putting the firewall first means that we can avoid processing RPCs that will just get dropped. However, these two configurations is actually not semantically equivalent. If the logger runs first, it sees everything. But if the firewall runs first, it may block certain RPCs, in this case RPC 1, and the logger will never see it. So reordering elements can lead to subtle changes in behavior, and when elements are stateful, these changes don't just affect one request, they can impact all future RPCs as well. So to preserve semantics, AppNet uses a symbolic model to track how each element transformed RPC and affects its internal state. The goal here is to check if two configurations will behave identically for any possible input RPC stream. First, a check for the output RPC stream they produce. In this example, both configurations produce the same output RPC stream, meaning that RPCs that reach the end are the same. It also checks the internal state of each element. And in this case, the top configuration block will not capture the result of the firewall, but the bottom configuration will. So the compiler concludes that those configurations are not semantically equivalent. And our paper has a proof of why such analysis is correct. AppNet implementation supports 3 processing platforms. And we also integrate AppNet control plane with Kubernetes to get runtime information like service location and available processors. Next, we'll move on to evaluation. We aim to answer 2 questions in the evaluation. First, is our abstraction easy to use and expressive? And can they reduce the overhead and improve the performance of application networks? So we surveyed popular search meshes and picked 12 commonly used ANFs, things like rate limiting, caching, and fault injection, and implement all of them using Envoy. Each took about just 7 to 28 lines of code. We were also able to implement 2 complex ANFs in less than 100 lines of code. Metaservice Router and Google's Preco are both deployed systems that handles routing and load balancing. And for comparison, we also hand-wrote the same ANF for each platform, and they took about 5 to 60 more lines of code compared to the AppNet version. And in addition, AppNet code is platform neutral, which means that developer can write it once and it can be automatically deployed across different platforms without having to re-implement it on each platform. So those results demonstrate that AppNet can greatly simplify ANF deployment. Now let's see AppNet performance. Since there's no existing benchmark for application networks, we created a corpus of randomly generated AppNet programs, each with randomly assigned order, platform, and placement constraints. We evaluate AppNet's ability to reduce RPC overhead using a simple echo server. We first compared it with a baseline that just ran the input spec as it is, with no optimization. So the figure here shows the median overhead reduction of AppNet with strong consistency compared to the baseline. And it showed that AppNet can reduce the RPC processing overhead for both metrics, both for latency and CPU usage by up to 47%. We also compare AppNet with local optimization, where we apply simple and local rules, like always choosing a platform with the lowest processing cost. This kind of mimics what the developer might do to manually improve the performance. And as you can see, it provides limited overhead reduction. Finally, when developers choose for weaker consistency levels in AppNet, they can get even better performance. Next, let's look at the end-to-end application performance on the hotel reservation benchmark. The figure here showed the application performance improvement compared to the baseline. And similar to the previous slide, we can see that AppNet can greatly improve the performance. Whereas the local optimization show limited performance. And finally, the weaker consistency levels yield greater performance gains. And with that, I will conclude my talk. Application networks are ubiquitous and they are hard to build today and have poor performance. AppNet provides a new way to program application networks. It decouples specification from implementation. It can automatically generate efficient implementations across different platforms. and it optimizes performance based on platform characteristics and user policy. And if you'd like to learn more or try it out, AppNet is available at those two links. Thanks for listening. I'm happy to take questions.